Magis Day, Ateneo Hearters, and welcome to our lesson on molecular geometry and polarity. In this video series, we are going to learn how to predict the shapes of molecules based on Lewis structures and decide whether a molecule will be polar or nonpolar. Okay. Now we have already drawn the LEDs of molecules and of polyatomic ions. They tell us the placement of the atoms with respect to each other. They tell us about the kinds of bonds that are present, but they can only tell us so much. All right. In reality, molecules exist as 3D objects. So that's why we have to consider their arrangement, okay, their 3D arrangement in space. And that is where molecular geometry comes in, which is basically a study of the 3D shapes of molecules. Now we start with this balloon analogy wherein if you have two balloons and if you hold them at this point here, you will notice that the inflated parts of the balloon tend to move away from each other. All right? And then if you add another balloon, they will orient themselves that way, and the same behavior goes on or is observed the moment you add some more balloons. Okay, and how do we relate this to the placement of atoms in a particular molecule? Okay, so in general, the shapes of the molecules are analogous to these balloons. Okay, we think of the center as our central atom, and the inflated parts of the balloons can either be our uh, non-bonding pairs, or it can be an atom in itself, an appended or attached atom in itself. All right. So this behavior or this particular arrangement is best described in the Vesper model. All right, so it's VSEPR, but it's pronounced as Vesper, which stands for Valence Shell Electron Pair Repulsion Model. Okay, so it says that the structure around a given central atom is determined principally by minimizing electron pair repulsions. So the important things that are mentioned here is that electron pairs repel each other, and that the arrangement of electrons or in a particular molecule will be that in such a way that the electron pairs repulsion will be minimized. Okay, since like charges tend to repel each other. So here is an example of the lens of water and carbon dioxide. Okay, you might have noticed that water is not written linearly, just like we usually do in LEDs. It is actually written, or the correct way of writing it is this one. It's actually bent, and we'll know later on why it's quite bent. While for carbon dioxide, okay, you do not see any non-bonding pairs of electron on the central atom, so it will retain its linear shape. All right, and then this has an effect later on the properties of the molecules. For example, why can why can water dissolve some substances while others cannot? All right, or why can't oil and water mix? So this has something to do with their polarity, the molecular polarity. Okay, and then we have here the steps for predicting the molecular structure using the Vesper model. So the first one is to write the correct Lewis structure. Okay, or in terms of resonance structure, we have to choose the best one. All right, and then we have to count the number of electron domains, okay, the total number of electron domains, which can either be bonding or non-bonding. When you say electron domain, that is primarily made up of uh, a pair of electrons, okay, or it can be made up of a single bond or a double bond or a triple bond. Now, one double bond is considered to be one electron domain, all right? And one triple bond is considered to be one electron domain only. All right. Again, so when you say electron domain, these are practically spaces where there are high electron density, okay, electron pairs. So it can either be a non-bonding electron pair, or it can be a single bond, or a double bond, or a triple bond. Okay. Now, the next step is for us to identify the electron domain geometry, or the EDG, which can be classified into linear, or it can be trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. All right. And then so in using the number of the bonding domains and the non-bonding domains, okay, we just change P here into D, we determine the molecular geometry. Okay, and so here is a schematic of the steps. So first is the LEDs, then the number of electron domains. After that one, we get the electron domain geometry. We get the number of bonding domains and the non-bonding domains so that we can get the molecular geometry. Now, in your module, we actually have this particular table. Okay, uh, we have the steric number, which represents the electron domains, the number of electron domains. So for example, we start with 2, okay, which gives us here on the first column are your electron domain geometries, the possible electron domain geometries. So the electron domain geometries are those that show us all bonding pairs, okay, all that are bonded. It doesn't show us any non-bonding domain. Okay, so in your handout again, this is your electron domain, number of electron domains, which can be 2, 3, 4, 5, 6. And then the basic geometry is practically our electron domain geometry. Okay, electron domain geometry, which gives us no lone pairs, okay, or no non-bonding pair. However, it could be that you can have three, okay, three electron domains, and then there is one lone pair, just like this one. Okay, so the dots here represent the non-bonding domains. Okay, the dots represent the non-bonding domains. And then we can have more electron domains, so 6, 7, 8, and so on. But in our lessons, we will just take up to 8, or until the octahedral electron domain geometry. Right? So in here, this gives us a practical example. So here we have a table detailing the number of electron domains, and then the electron domain geometry, which is our EDG, our bonding domains and the non-bonding domains, and our molecular geometry, and a few examples also. So here, for example, you have 3 electron domains. So BF, okay, boron trifluoride. One single bond is an electron domain. So if you count how many electron domains there are for boron trifluoride, you have 3. Okay? If you have 3 electron domains and no non-bonding, so meaning there are no free electrons there, free pair of electrons, then we consider the molecular geometry to be trigonal planar. Alright, so your clue will be, if there is no non-bonding domain, the electron domain geometry and the molecular geometry will be the same. Okay, again, if there is no non-bonding domain, you do not see any free electron pairs, then the electron domain geometry is the same with the molecular geometry. Now, let's take another example for this ion, okay, the NO2 minus. So you see here that this is made up of, again, a double bond is one bonding domain. So this is 1, then 2, okay, there is a non-bonding domain, and 3. So there are 3 electron domains, but out of the 3 electron domains, there are 2 bonding domains and 1 non-bonding domain. Okay, so there is now a 1 electron pair present, and take note that that electron pair will repel the attached atoms. Okay, will cause an arrangement that will minimize the repulsion between the electron pair and the atoms. So that's why there is another molecular geometry associated with it, and we consider it to be bent. All right. So you notice that the molecular geometry will also depend not only on the electron domain, but also on the number of the non-bonding domains. Okay, another example is this one, NH3. This is ammonia. All right, so if you draw the lens of ammonia, you have four electron domains, and then you notice that out of the four electron domains, there are three bonding domains and one non-bonding domain. Okay, and so that gives us an electron domain geometry of tetrahedral, but the molecular geometry is trigonal pyramidal. All right, so you need not worry. You can actually use your table for the one that is given in the handout. Okay, or you can use this table to refer to your answers later on. Okay, so and we go back to the example that we had. So there will be more instructional videos for some examples later on, but we go back to water and carbon dioxide. So for example, in here, water, the number of electron domains is 4. So this is one electron domain, another, this is your third electron domain, and this is your fourth electron domain. So that's why it is 4. Now, if you have four electron domains, then our EDG is tetrahedral, as what is found on the table. Okay, so tetrahedral, that is like a shape in a steering wheel. However, we notice that there are only two bonding domains present, so two domains present, and there are two non-bonding domains. Okay, so therefore, our molecular geometry is bent. All right, so bent. So if you try to go back for tetrahedral, if you have this combination, two bonding domains and two non-bonding domains, you have a bent shape, bent molecular shape. Now, in the case of carbon dioxide, so again, a double bond and a triple bond is considered to be one domain. So if you have this structure, you can count one, two electron domains, right? So there are two electron domains for carbon dioxide, and then the electron domain geometry there is linear, and we do not see any non-bonding pair or non-bonding domain. So the same molecular geometry is the same with the electron domain geometry, which is linear. All right. So there will be more exercises later on for electron or for molecular geometry. So stay tuned.